forces. Resultant forces means it's sum of all forces that's acting on any object. Sum of all forces. So that is what resultant forces means. But before that, we need to really look at some of the terms which are used to describe forces, which are listed here. Push. So push being one, and which is some, imagine you push an object, which is maybe a shopping trolley. Pulling, pull a door handle as an example of that force. Thrust is used to describe a force possibly from an engine of a car. So, or you can even use that for any push force, normally used to describe the push of an engine. Friction is the force acting between any two objects in contact and it's moving with respect to each other, possibly both of them moving in opposite directions, or one of them moving on top of the other one, rubbing against the second surface. So there are two surfaces that are moving, and this acts opposite to the direction of movement. So that's something that you can remember. So it's opposite to direction of movement. We'll look at some examples, then you'll understand that better. Okay. All right, so that's what friction is. Air resistance or drag. Air resistance acts on any object which is trying to move through air. Particularly when it moves faster, air resistance force increases. So again, we'll look at some examples to illustrate that, air resistance. Drag is another word which can be used instead of air resistance, but it's preferable that if you use drag to describe the force acting opposing any object that is moving through water. Okay, so air resistance and drag both opposes movement of objects through air and water. Tension is a force that acts on strings and things that objects are hung on. Okay, so that is tension force. To give an example, imagine you hang an object down on a string like so. So that can be a ball or an object that's hanging on a string. The weight acts downward always, so that's weight. The tension acts opposite to that. Okay, so that's tension, which is on the string, which actually balances the weight force. Okay, on a surface or on Earth or on any other planet, except in deep space. In empty space, there is no weight. But if the object is on the surface on Earth anywhere, weight acts straight downwards towards the center of the Earth. So that is something to remember. In space, objects don't have a weight, and this is often confused with mass. Now, mass is actually not a force. Mass remains the same wherever the object happens to be. But weight is related to mass, but it is to do with the gravity and mass together. So it's a product of mass and gravity is the weight. Okay, and weight is a force, mass is not the force, gravity alone is not the force. The gravity acts on an object, which then puts a force on where it is sitting or standing. So it is true for any object that's standing on any planet which has got gravity. So gravity causes the weight, which is the force. Now, we'll learn about weight a bit later, but for now, you need to remember the direction of the weight is to straight down towards the center of the Earth. Upthrust is a force that acts upward on any object that is actually floating in the air or inside water or even on floating on top of the water. So it is an upward force that acts on objects which is in the air or floating on water, on the surface of the water, or inside any object that is inside water, immersed inside the water. Upthrust will act on them, pushing the objects upward. Okay, so these are the terms that we're going to look at. These terms are used in with relevance to resultant forces. So we're going to be focused on resultant forces, but we're going to use these terms all through this topic. So make sure you're familiar with these words which are used to describe forces. Okay, let's apply some of the ideas that we've learned so far, and let's consider this case where a cyclist riding on a flat road like so. One of the forces we should be able to recognize straight away is for any object on any planet or on the surface of a moon will have any object which is got a gravity will be the weight which is acting straight down towards the center of the planet, and here on Earth it is going to be the center of the Earth. So this force acts towards the center of the Earth, and that's the weight. And for the weight or for any other force, we also have one opposing force which is called the reaction force. Okay, so that's reaction, which is equal in size to the weight. So whatever weight you have a reaction force. This is actually true for any force. So if you apply a force on any object, you're going to get an equal and opposite force in the opposite direction, and that will be called as reaction. And you should also recognize all forces comes in pairs. So for every force that you have an equal and opposite force that is acting on the other object. So this is the force, the weight is on the floor, and this reaction is on the bicycle. Okay, so the weight is also on the bicycle as well. So there are two forces that's acting, weight and the reaction, which balances the bicycle in that direction, in the vertical direction. So let's have a look at the other forces that's involved here. Okay, so the wheel is spinning that way. If you observe a cyclist riding, the wheel would be spinning that way. Obviously there is a push force, the pedal is being pushed in that direction. It's not shown here. Let's not label too many forces, that will be confusing. So we have this pedal force, and that's going to be the wheel that is spinning in that direction. Okay, so I'm going to label that spinning direction and show that with an arrow like that. Okay, and we know the friction force is going to be always opposite to the direction of movement. So in this case the wheel is moving backward, so which is that way. So that means the friction between the wheel and the floor is going to be in the opposite direction, so which is that way. So that blue arrow represents friction. Okay, and that acts in an opposite direction to the movement of the wheel or any two surfaces that is in contact and rubbing against each other. Okay, so in this case it will be forward. Now it's hard to see it, but this is the actual friction force. This is the force that actually helps the cycle move forward. Now that may come as a surprise, because we know friction is being a nuisance and stops us from moving forward. We always try to minimize the friction, but in this case, without friction, the cyclist will not be able to move forward. And if you think about this, riding a bicycle on an icy road is going to be very hard because you don't have a lot of friction. So friction is necessary between the wheel and the road to move the cycle forward. There is another friction force here between the wheel and the axle. There is a rod, and that friction is not very helpful. That friction is going to be slowing down the cyclist. It's going to work against the movement. Okay, so let's ignore that friction for the moment. Let's just consider this. We can draw a very small arrow for that friction. Okay, like so, and it's okay. So that's also there. Let's label that as F for friction. There is also another friction, and here is another friction. Okay, so we'll have to consider all these forces. We also have air resistance acting on the cyclist if we consider the cyclist moving and at a steady speed, moving forward. So we have air resistance here acting. Okay, and pushing the cyclist backward, and that's not helping him to move forward. Obviously, when it goes faster, the air resistance will get bigger and bigger. Okay, that's something to bear in mind. Okay, so obviously you need to have a bigger friction force than the air resistance, and we'll come into that when we actually look at resultant forces. And what we're looking here is just the names of few forces and the direction in which they act. Bear in mind, this friction is helpful, that friction works against the movement, and it's not helpful. It's going to work against this friction force in how the bicycle moves forward. Okay, so we should be able to recognize this force, which is the weight of the scuba diver. Okay, weight goes straight down as always. And will you have another force against this? And that will be upthrust this time. Okay, because she is inside. Let's consider that this is a lady. So this person is inside water. So there will be a force of the water pushing the person upward, and that will be, if the person is not moving up or down, they will be equal. Okay, so if the person is like moving forward or backward and not moving up or down, so then you know these forces are balanced, they're equal. Okay, so then we have the person pushing on the water, and this is interesting and also a bit tricky to understand. So really make sure that you understand this. The person is pushing the water backward. Okay, so how come that helps the person to move forward? Because the water will then push the person in the forward direction with an equal and opposite force. So make sure that you understand that. Person is pushing the water backward. That's why I've drawn the arrows with equal size, so it makes sense, because these forces are indeed equal. Okay, so this force, mind you, it's on the person on the water, and this force is the water pushing the person in the forward direction. So this is the only force on that person. Okay, now the effect of that force, now as you can see, will be moving forward. Now you have to consider the drag as well. So let's draw the drag force. Okay, now for any object that's moving through air or water, so they'll have the drag force, so acting that way. Okay, so there'll be, now I've drawn this arrows deliberately smaller to consider which force is now bigger. Now obviously the blue force, which is the blue arrow showing the forward force, the push of the water on the person is bigger. So if you consider that and compare that with that, ignore this because that is the person's push on the water. So this is the water pushing that person. So this is actually the push forward force, if you like. This is the backward force. Just consider these two. You can already see this is bigger, so that will have an effect on that person. That person will move forward, will accelerate. Again, we'll come back to that idea later on, but for now you need to make sure that you understand the direction of these forces. So this is the push of the water on the person. So I'm going to label these forces so you can see. Okay, I've labeled these forces now. You should be able to see that is the push of the water on the diver, and that is the force that is going to move the diver forward, as that is bigger than the drag. Now this is the push of the diver on water, so this is not on the person, on the diver. These forces are equal, so the diver will not be moving up or down, but will be steadily moving that way. Again, we'll revisit this briefly in a minute. Okay, let's look at another example here, where I hope you can see a boat is pulling a skier, water skier, who is attached to the boat with a rope, with a string. Okay, and you can also see a propeller here, which spins to push the water backward. So that force I'm going to show as the boat, the propeller, the fan, which is at the back with the help of an engine, is going to push the water backward. Okay, how come that helps the boat move forward? Because the water, as you know from the previous example, is going to push the boat forward with an equal force, but this time it's forward. And you need to be very specific here. It's the water that is pushing the boat in the forward direction or in the opposite direction to the push of the propeller on the water, and that should be very clearly understood. Okay, so you have also the boat pulling the skier in that direction, so that's a pull force. Okay, so you have a pull here. The skier, on the other hand, there's going to be an opposite force in the opposite direction, so that's going to be the tension. Okay, so that's going to be in tension on the rope or on the string. Okay, so you have that there. All right, so you have so many other forces. Now we don't have to show all the forces all the time. Of course, you have the weight and the upthrust, so weight and upthrust is there. Okay, and as I said to you, not all the time you show all the forces. You have the force of the engine, which is that push over there, it's already shown, and that is the force of the push of the water on the boat. You will also have the drag, which is not shown here. So if you want to show the drag and the air resistance as well, so you have the air resistance. It's quite a lot of forces that's acting here. So in this case, the air resistance has to be very small compared to the push of the boat. So I'm going to make this as small as possible. So that's air resistance. Okay, and I'm going to make this arrow slightly bigger to actually emphasize that this is actually bigger, obviously, because otherwise the boat can't move forward. Okay, the air resistance is pretty small, so I'm going to draw that over here. So a small air resistance here, and you can also say a small drag force is also there in water. Okay, so there is a small drag force there. Again, the sizes are important. This force, the forward force, is much bigger than the drag force and the air resistance, the drag and the air resistance put together. So we'll put some numbers to this, but for now, the direction and the names of the forces, and it's the understanding of that this forces comes in pairs. As you can see, if you push the water backward, the water is going to push the boat forward, and realizing these things are really important to understand the resultant forces. So just to remind ourselves, resultant force is a sum of all forces acting on an object. So in this case, we're going to have a look at an example of a car, and we're going to have some forces actually shown here. Okay, so let's have a look at the forward force of the engine, and I'm going to label that as, I'm going to show all the forces. Let's just look at the engine force, and let's say that is 1300 newtons. Okay, so that's the forward force of the engine of this car, and the friction is here, so let's say that is 200 newtons, and the air resistance is a bit smaller than that, so I should have drawn an arrow smaller than that, so it's slightly smaller, and that's say 100 newtons. Okay, so you have friction 200 newtons, 1300 newtons forward force of the engine, the thrust force. And so what's the resultant force here? Now what you need to understand is you can have the forward force as positive and the backward force negative, even if the question doesn't ask you to give doesn't give you the signs of these forces. So we can assign for the sign to the forces depending on the direction. So let's have the forward direction as positive force and the backward as negative. So all we have to do is add them up together. So if you add 1300 and add these two together, all these three together, you have the resultant force as resultant force in this case is 1300 take away 200 and take away another 100. So in effect what you're doing is you just punch these numbers in the calculator and you should get the answer. So 1300 take away 300 newtons, and that gives you 1000 newtons forward. Okay, now you may understand, you may wonder, have I included all the forces? Now, of course, I have not included the weight and the reaction force, because as we know, they're going to be equal. So they're going to cancel each other. The sum of these two forces in that direction is 0. So the only forces to consider is what's forward, what's backward, to decide what's going to happen now. So you have forward force of 1000 newtons, and this shows the forces are not balanced. Now, there are two different cases what will happen to the car in this case. We'll come to that later on when we look at force and its effect on the movement of the car later on. But for now, I hope you understand the resultant forces in this case. Okay, let's have a look at this happy guy who is driving the boat on the water. So let's have the forward force of the engine. So in this case, the engine is here. So I'm going to draw the forward force provided by the engine like over here. Okay, so that's the push force of the engine. Okay, let's label that as thrust. Okay, and then you have the drag force provided by the water. So that's going to be drag in the opposite direction, drag. Okay, so let's give some numbers now. Thrust, let's say 1750 newtons. Okay, so that's thrust, 1750 newtons, and the drag force is say 300 newtons. Okay, so what's the net force? There is no other friction that's there, it's just the friction drag of the water. Let's have some air resistance as well. Okay, so air resistance is moving pretty fast. So air resistance in this case is going to be 200 newtons. Okay, slightly smaller than the drag. Okay, so there you have what is the resultant force in this case. So as usual, you can have the forward force or as positive. So I'm going to have that force, the thrust force as positive, 1750, 1750 newtons. Okay, take away this force, 200 plus 300, that's 500 newtons. So I'm going to take away 500 newtons, or you can do that individually, so you'll have the same answer. You take that away, you get 1250. I hope I've got this right. Yeah, 1250 newtons, and that is the resultant force, and it is in the direction of the forward force. And it's really important in the exam, and you are expected to say the size of the force and the direction of the force. So in this case, the size of the force is 1250, and it is in the forward direction. Why is it in the forward direction? Because you got the bigger number winning. In this case, the bigger number is 1750. So the resultant force is going to be in the direction of the bigger force. So that's why you take away all these numbers and you say that is going to be in the forward direction, or you can say from towards left, because on the picture as you're looking at it, it's towards the left. Okay, let's consider this case where this guy is trying to push the box forward against a friction force. As you can see, the friction force is between the moving surfaces. Now he's trying to move the box forward. As you know, the friction is going to act in the opposite direction. So you have the resultant force here, 300, take away 175. So what would that be? So you can pretty much work this out. So you can give this a negative number, minus 175, because that's you're going in that direction. You can consider that as positive, and this is negative. So you put minus 175, you get 125 newtons forward. Now the effect of that will be, so you can see the force in the forward direction is bigger. So this force is going to be in that direction. Because that's bigger and it's not balanced by the backward friction force, the box will actually move forward and accelerate. Again, we'll come back to that in a minute. When we look at the effect of the forces, effect of unbalanced and balanced forces in a while. Okay, let's consider one last case before we go into the effect of balanced and unbalanced forces. So let's consider the weight of the ball is always there, even under the water. So that's going to be 2 newtons. And the upthrust in this case, because you can imagine with the ball filled with air, the upthrust is going to be much bigger. You can almost predict the ball is going to bob upward, bounce and move upward in this way. So your upthrust is going to be like more than 2 newtons, so let's say 5 newtons, you can see the net force, the resultant force, is going to be acting upward because that force is bigger. And to calculate that, it's pretty easy. 5 take away 2 newtons, so it's 3 newtons upward. So all you have to say is resultant force in this case equals 5 take away 2, that's 3 newtons. Easy, resultant force is easy. Okay, so we're going to look at now the effects of these forces. What's going to happen to the objects is the next thing to look at. Okay, let's consider the effect of these forces. Okay, so we're going to be looking at what happens to the object as a result of the any force that's unbalanced or balanced force acting on the object. Okay, so first some words that are very often used. Stationary object means it's not moving and it's at rest. Also means that it's not moving. The speed is 0. Stationary, not moving, at rest, all mean the same thing. Speed is 0. Steady speed is the same as constant speed or uniform speed, all meaning the same thing. They mean that the object is moving at a same speed. Speed is not changing. That's what it means. Okay, so let's consider the same example as before, but in a different way. Okay, so you can see here the forces are shown. Now you have some air resistance, some forward force of 1700 newtons. That's the push of the boat, of the engine, and you have the drag and air resistance acting. So imagine the net forward force, the force of the engine is 1700, and all of this put together is 350. So you can pretty much see the net or the resultant forward force is 1350 newtons. You just take away that. Okay, so if you got that, what is the effect of what will happen to the boat? Now, two things, if it is already moving at a steady speed, the result of the effect of that force is the speed has to change, and in this case it's obvious to see that the speed will increase. In other words, it will accelerate. So the boat will accelerate. That's the effect of the net force on the boat. And obviously the person who is skiing as well, that person will also accelerate together with the boat. Okay, so that's the effect of that force on the boat. So there are two cases to consider. Are the forces balanced or unbalanced? So question to ask before you can decide what will happen to the object. So in this case it's a car. Is it stationary? Is it already moving? Now, if the forces are balanced, there will be no change in speed. So that is something that you need to understand and make sure that you apply that. So there will be no change in speed, no acceleration, no deceleration, no change in speed or direction. Okay, so if the forces are balanced, there will be no change. That's a rule that you need to apply. Whether it's already moving, then it keeps moving at the same speed. If it is stationary, which means it's not moving, then it will stay stationary, stay put at 0 miles per hour. So it's not going to increase its speed. So balanced forces, no change in speed or direction. Basically no change. If the forces are unbalanced, then you will have a change in speed. So that is something that you need to apply. So whether it's stationary or moving, there will be a change in speed or direction. That will be the effect of unbalanced force or direction. Okay, so if you apply this rule carefully, then you should be able to decide, no matter what the situation is, you should be able to say this is what exactly will happen. Now when you talk about change in speed, if it increases, now it can go either way. It can increase the speed or decrease the speed. Now we know increasing speed is, we term that as accelerate. So it will either accelerate, okay, or decelerate. Decelerate means slowing down. Okay, so one of this will happen. Okay, so bear that in mind. So two cases. Okay, one is unbalanced. So if an unbalanced force is acting on an object such as a car, then it will either change in speed, which means it will accelerate or decelerate, or it will change in direction. So make sure that you apply this rule. Okay, let's actually look at an example. In this case, the guy is pushing the box with a force of 150 newtons, and you can also see 150 newtons of friction force acting backward. Now, what will be the effect of this on the box? Now, obviously, the forces are balanced, and not to mention the weight as well as the reactant force. Let's ignore them completely because they're going to be equal. You don't have to work that out. But let's consider just these two forces. They are equal, they're balanced. So the effect of that, if you apply the rule that we've just looked at, there will not be no change in speed. So if the box's initial speed is 0, which means it's not moving anywhere, staying put. Now, because although he is pushing it forward, you can see the friction force is balanced with that one. So the net effect is the box will not move anywhere. So applying the principle, the rules that we've just learned, if it is stationary and if the forces are balanced, there will be no change in speed or direction. So the box doesn't move anywhere. So in other words, the speed of the box doesn't change. Same guy now is increasing the force to 300 newtons. The box, now the friction force also increases to 300 newtons. Can this happen? Can the friction force increase? Yes, it can. Okay, it can respond to your force. Now, friction force can increase, and there's a limit to how much the friction force can increase. But that's something to bear in mind. Friction force can increase. Okay, so still it's balanced. So the resultant force, the effect of the resultant force is that resultant force is 0 because 300 take away 300 is 0. So the box speed does not change. It's staying where it is. Okay, now the guy has increased the force to 500 newtons. Now the friction stays at its maximum of 300 newtons, doesn't increase anymore. So what will happen? What's the resultant force? Now you have 200 newtons in the forward direction. So that's the resultant force. What will be the effect of that on the box? The box's speed has to change now. Initially its speed was 0. So that's the speed at the start is 0. Now it has to be more than 0. So the effect of that force is the speed increases, okay, or it accelerates. Speed increases, okay. Or you can also state this more simply, that the box will move forward. So let's consider this guy who is driving this car with a forward force of the engine, 1500 newtons is the forward force of the engine. Now you have an air resistance of 1300 newtons. He is going pretty fast, so the air resistance has increased to this amount. Okay, so it's very close to this. Now the friction on the wheels, which is not helping it to go forward. Remember, there is another friction force here as the wheel is spinning backward that way. The friction force is acting. We're not talking about that friction. We're talking about the friction in the wheel and the axle, which is actually the rubbing of the wheel on the axle. So, and also there are, 4 wheels there, so there's going to be friction, which is going to go against the movement. So that's 200 newtons. So now you can see the resultant force is going to be 0. So in this case, resultant force is 0. Okay, 0 newtons. So what will be the effect of that on the car? Will it go faster? Will it keep going at the same speed, or will it stop? Now, remember, he's already moving at 70 miles per hour. The forces are balanced, so the effect will be, apply the rules, there will be no change in speed. So, no change in speed or direction. If the forces are balanced, apply the rules, no change in speed or direction. So, he will continue to move, the car will continue to move at 70 miles per hour. That is the effect of having a resultant force on an object which is already having a uniform speed of anything. In this case, it's 70 miles per hour. Let's consider this case where a skydiver is already coming down with the speed of, let's say, 30 miles per hour. So 30 miles per hour. And because he's already coming down at a uniform speed, okay, now suddenly he opens up his parachute, obviously to slow down. Okay, so he's just deployed his parachute. He's opened up the parachute. It wasn't open before, and he was coming down at 30 meters per hour, 30 miles per hour speed. Okay, so what will be the effect of the forces now? Have a look at the forces. The only force that's acting downwards is 800 newtons. And now, just because he's deployed the parachute, the air resistance has now increased to 3,500 newtons. Okay, so it was 800 newtons just before he opened up the parachute. Now it's 3,500 newtons. What will happen to this guy or the person? So what will happen is, because this is bigger, the resultant force is upward. Now 3,500 take away 800 newtons. So that will be 2,700 newtons. 2,700 newtons. Now this time it's upward. Okay, so you need to state the direction. That now it's upward. Now, will the person start moving upward? Not really. The person is already moving downward in this direction at 30 miles per hour. So the effect of that unbalanced force, now the upward force, is that he will decelerate. So the speed will change if you apply the rules we learned. Unbalanced force, the speed has to change. But if you apply logically, what should happen is, as the person is already moving downward, the speed will now decrease and the person will decelerate. That is the effect of the unbalanced force on the person. Okay, so decelerate, right? So this plane is flying at a uniform speed. The pilot wants to land the aeroplane on a landing strip, on the runway, and the lift force is the force on the wings provided by the engine. Okay, so you need to say at the moment, as it is flying now with a uniform speed at a certain height, the height is not changing, what should the lift be? What should be this force here on the wings, on both wings, obviously, put together. Now consider the weight of the aeroplane. Now you can pause the video, think about this, think of an answer. So the lift force should be exactly the same as this. So 390,000 newtons to balance the weight if it has to fly at the same height. Now the forward force is the same as the air resistance. That means the airplane is going to have a steady speed and it's going to fly at a certain height. Now consider this question. Now the pilot of this airplane wants to land this now. So how the forces should change? Now he has to slow down the airplane first. Now he can't land the airplane at the same speed as it's flying. So in order to slow down, what forces need to be changed? If you want to pause the video now, pause it, think of an answer and check your answer in a minute when you're ready. Okay, so the forward force has to be reduced, and what the effect of that would be, the aeroplane will slow down in the forward motion, so it will slow down the speed, and also the lift force needs to be reduced gradually from here. Okay, so you have to go lower than 390,000 newtons, so the aeroplane can actually start coming down at a steady rate. Okay, so it has to lower its altitude in order to land. So this force needs to be reduced. So have a look at these forces and think about the movement of the aeroplane as a result of these forces. What will be the effect of these forces? This is a very hard example, and first of all I want you to consider the two directions. One, the resultant force in the vertical direction and the resultant force in the horizontal direction. So let's do that first. Now if you look at this force, the lift on the wings, it's 370,000, and it's much bigger than 290,000. So you can imagine the effect of that force is going to be the plane lifted upward. However, you need to consider the horizontal component of the forces as well. So there are two forces acting horizontally. This is the air resistance, and that is the engine's thrust force. So you have 300,000 newtons acting in the forward direction. So you have to resolve this in two directions. One's vertical and the horizontal. Okay, so take a few moments to think about the two answers. One is vertical, the other one is horizontal. So you should have got this answer now. In the vertical direction, you should have got 80,000 newtons as a resultant force. So you have 80,000 newtons in the vertical direction, and in the horizontal direction you should have got 278,000. So in the horizontal direction we have 278,000 newtons. Okay, so that is in the horizontal direction. Okay, but what is the direction of the resultant force and how much is it? So let's have a look at that. And this is a very, very hard example. Normally in GCSE exams they do not expect you to go into this much detail. So this part is only for those who are really curious. So you must have worked this out by now. You got the vertical force, resultant force is 80,000, and your horizontal force is 278,000. Now, what's the direction of the resultant force? We still have not worked out the final resultant force will be. So if you move the smaller force at the end of the bigger force, what you end up is a triangle shape. And if you now connect the start and the end of that triangle, you get the direction of the resultant force. Now you can also work out the size of this force, but that's beyond the scope of this video. But if you use Pythagoras, and if you can do simple calculation using that square and take the square root, you should get the size of that. But the direction, again, you get the angle here, and that will be the direction of the resultant force. So the actual aeroplane will be moving in that direction, as you can see, in that direction. As I said to you, this is beyond the scope of GCSE, but it's good to know that you can have a resultant force in between the two forces acting, if there are two forces acting on an object at the same time, as in this example. So you should be glad to know that is the end of resultant forces. So take a break, and well done for completing this tutorial.